together, and in this class for this semester, we're going to talk about CEN 105, discussing about linear algebra. My name is Arban, so you can see the information also in the syllabus that I just shared with you. And we will be covering the theory of this course, and together with me, you'll have Joanna that will help you in the seminars. So this will be two individuals with whom you are going to have some contact during this semester. The class is linear algebra. These are the names of the instructors. And the next important piece of information is the textbook. And regarding the textbook, we are going to cover or to use as a primary source. We are going to use this textbook, Anthony and Harvey. So there are two authors of the book of linear algebra. And you can track the textbook based on the names of the authors who authored the book. So this is really a good book. A classical one, but at the same time, I strongly suggest also another book written by Gilbert Strand. So this is also a classical textbook, and while the topics that we're going to cover in the class, they will be ordered according to this textbook written by Anthony and Harvey. I strongly suggest you also to go over the problems that are listed in the book of Strand, which is also titled Linear Algebra and Applications. Something. Okay. Okay. So this will be the basic information that you should know. Meanwhile, you can get these textbooks from the library. Okay. So you can find them there. Or you can even purchase them from the respective publishing houses. And first of all, I just want to clarify a few things. So this course is called Algebra, and algebra it's a very broad topic, and it can even cover topics including group theory, or which can be found in abstract algebra. And but this is mostly needed for students of pure mathematics. For engineers, we don't cover that abstract algebra part, but we just cover here in this course the linear algebra. Now, linear algebra, the key word linear here, what it means any relationship which regard to 3x plus 4y is equal to 5. So this is linear algebra because all of these variables, they are to the power 1. Okay, so this is a linear relationship. Anything that looks like 3x squared plus 4y cubed is equal to 7. This is not anything related to linear algebra. So that's what I can say about so far. And then we can generally also ask the following question. How difficult would this course be? First of all, I can ask you actually, what do you think? Would you expect this course that we just started today, would you expect this one to be an easy course or a difficult course? What is your expectation? Can you write this one in the comment section of this class or in the chat section? You just write down easy or difficult. Okay, you select one option, you go with it. What is your expectation? Your comments in the comment sections will also count like your attendance sheet. So being active with comments here, I will decide if you were present. Something in between, okay, moderate level of difficulty. So Cindy is expecting a moderate level of difficulty. What about the others?
I think it would be easy because we don't have to deal with the powers of x and y.
Okay, that's fair enough. Okay, so we have I see some comments down here. So something in the middle, that gives a run. We have good number of fans around here. Easy, maybe, medium, yes, okay. So it looks like we have also another scale, apparently easy, difficult, and maybe we have also moderate level, so let's call this 3. Okay. So this is what you are expecting. And I can also ask you the following question. What would be your expected grade in this course? So let's assume you can get an A, which is a 10, you can get a B, which is a 9, you can get a C, which is somewhat like 7, you can get a D, which is around 6, and then grade letter F, which is anything from 0 to 5. What would be your expected grade in this course? So I can also expect a few comments in the comment section. So you started the university degree, and linear algebra is really a very essential, formative piece of class. But what is your expected grade in this class? So can I have your expectations? Okay, there, started first. Being high, expecting a good grade, but being realistic at the same time. Something more, hopefully 8. We all hope for good. Okay. So we can get a distribution. Now I have the monitor far away from the camera, so I'm just moving back and forth the same way like Benefit Zero. If you see Benefit Zero Topinion, he just puts on a reverse gear, he moves backwards a few meters up to the point that he's going to hit his screen. But I'm doing this because I'm trying to read your comments. Okay, so we have some great distribution around here. So then we can also scale this. So this, if somebody is expecting an A, we can give this a score of 5, B, 4, 3, 2, and 1. Okay, so we can scale this down. And then we can also expect in this class, for example, we have around 50 students, and we can have here 1, 2, 3, 4, and 5. And then I could have drawn this better. And then the level of difficulty, that's easy, 1, moderate difficulty, 2, and 3 is the difficulty level as a function of the grades. So now, assume for a moment that we have a student 1, that expects a difficulty level of 1, which is easy, and also at the same time expects to get a grade of very good grade 5. Okay, that's student 1. Then we can have another student 2 that expects this course to be moderate level of difficulty, and because of being realistic, he or she expects to get a B. Okay. Then we can get another student 3, who expects this course to be easy, and he can have a grade of 4. Similarly, student 4, we can have a student that thinks it's easy, expects an A. So here, this is how we can plot a series of data. So, and the way of plotting this data in this way, it is equivalently to a vector. So here we have a vector which is pointing to a level of difficulty of 1 and expecting a grade of 5. So here we can find this student somewhere here. Okay, and we can draw here the vector which is pointing. So this is the first student. The second student who thought that this class is moderately difficult and expecting a B, we can find the student somewhere here. Okay. So we are using plotting of this situation of the students. The other one is 1 to 4, 1 to 4. So here we have better. I could use. So 1 to 4 is another student that shows up somewhere here. Okay, and then we have another student which is 1 to 5 and so on. So we can even have a student who thinks this class is very difficult and is expecting to get a grade of D. Okay, so we can even have a student that appears around here. Now, then the next question can be the following, actually. So first of all, representing types of data like this, these represent vectors. And in linear algebra, we're going to deal a lot with vectors. Probably the more generalized version of vectors, which would be the matrix, but we'll give the explanation regarding these in detail. Now, once you see this data set, the first thing that might come to our mind is the following, because we can classify students, good or bad students, or successful and non-successful students based on the grades. But once we give metrics like these, so these vectors, we can call this a metric, okay? A metric which is used to measure a variable or to quantify the situation of a student. So once we see this graph here, the first question that will come in mind is that how can we cluster these students? How can we put similar students in a common set, okay? Of course, there are several combinations, but once we look in here, we can even have another student that scores is afraid he or she is going to fail because the class is too difficult, so the grade corresponding to 1 would be a grade F here. Then probably somebody could say that, you know, these students that appear in this range, we can cluster them together based on the expected success in the class, and these two, they can also be clustered together. So students that think that the class is easy and they can score a grade between A and B, we can cluster them together also based on the reason that the vectors are very much similar to each other, or the angle between these two vectors is small. So in this case, we can say that they can be in the same class, okay? Now, and then again, if we are using vectors, we can say that two vectors are similar to each other if the angle between those is small, but a vector here is relatively different because the angle between these two vectors is different. Now, so this is a metric. Actually, a metric is the metric which calculates how similar two vectors are with respect to each other. In principle, actually, how close two vectors are with respect to each other, we can always subtract these two vectors with respect to one another. And if you see a small vector, that means a small difference, and so on. But so far, what we're trying to clarify here is that it is possible to represent not only two data sets, but two data, but also other variables. We can add them together, and we can construct even much more complex vectors. So, for example, we can have another student who thinks the class is moderately difficult, expects a grade of B, 4, but finally he might get a grade of A, 5. So we can expand this vector into 3 different variables: expected difficulty level, expected grade, and the grade the student achieves at the end of the semester. So we can add more variables here. So this would be the grade of linear algebra. At the same time, we can add here the grade of calculus. This would be the grade of English course, getting a 4. So these are the vectors with which we are going to work this semester. And this is one way how we can quantify student selections. And when we talk about quantification, this is similar to when you go to a doctor. The doctor says, "How do you feel?" You say, "I feel very well, thank you." And they say, "Can you tell this on a scale 1 to 10?" And you say, "Okay, I feel well. On a scale 1 to 10, I can score an 8 or a 9." So this is just how we try to quantify certain variables. And now, the reason we do this is that we often want the computers or the machines to provide a quantitative analysis about a certain situation. And a good example of this one is let's say, when we compare human vision. Human vision, we are very good at giving qualitative answers, such as what you can tell, for example, what type of flower is this? You can have a look at it, and you can also compare with a different flower, and you can classify them whether they are very similar to each other or not. Often we want the computers to do the same thing, to quantify certain aspects for us, and this the thing is that for a computer, in order to distinguish between different objects, if you show the computer an image, what the computer is going to see is going to be arrays of numbers, okay? So this is what the computer is showing. So this is 255, 117, 118, 111, whatever. So then you are showing this array of numbers or matrix of numbers, and then maybe you are trying, these are the numbers that represent 3. Okay, so imagine now you show to the computer an array of numbers, and the computer has to figure out that it's looking to a 3 or to an individual. So imagine that the self-driving car, they are provided with cameras and with machine learning enabled algorithms, which after they are trained, they are trying to classify every object that they see. So each moment, all they see is actually these numbers. And imagine for a moment, we are showing these, and then the car is deciding whether it should stop or should continue based on an obstacle that is observing at the front. Now, how is this made possible? You are given a matrix to say this. The way to distinguish this is that machines continuously try to extract patterns based on algorithms that we have written in a correct way. And these matrices that are provided to a machine or to a computer, they continuously try to extract feature vectors. So computers, they try to extract feature vectors. Okay, so it extracts the feature vector, and then in the data set, it has also several vectors, which say that if a vector is, it has these features, and this is also a feature, okay? Then the computer might say, okay, this is a 3. If there is another feature vector that could correspond to a person, to an individual, to a human, that would be a different feature vector. Now imagine cameras or vehicles will continuously extract some feature vectors, will compare, and similarly like here, it will try to allocate itself where it's going to be. Okay, so this is what is going to what's going on with the automated machines or vehicles. So these data sets, which can be provided as we wrote these on the board, these are principles that we can learn or we can use if we know some basic knowledge of linear algebra. Now, this is just something in general of what can be done with linear algebra. Now, when you ask me the question about whether it's going to be expected to be easy or difficult, I can also ask you this. Linear algebra, it's all about this. 3x is equal to 6. That's it. This is linear algebra. Okay? It's not any more difficult. So if we know how to solve this problem, 3x is equal to 6, then we are in good shape because we can simply solve a lot of complex problems. Now, this 3x is equal to 6. The question is, this is an equation. An equation, by definition, it's a relationship which has at least one unknown. Okay? And in this case, what is the unknown? We look at this equation, we say that x is equal to something, and apparently x is equal to 2. We did it. Okay, so this is how difficult linear algebra is. And then in linear algebra, any problem, it can be represented like this. Ax, this is equal to b. This is linear algebra. A is a matrix, x is a vector, and b is another vector. So here we give where a and b, they are given parameters, and the question is to find x. So this is all problems that can be solved with this aspect of mathematics. And now we can also add the following: that these operators that we do see here, that can be written into such a form, they can involve anything that you can see in mathematics. This semester, you are taking calculus, and in calculus, you are going to learn, for example, the first derivative, the second derivative, and similar concepts. And now, the first derivative, the second derivative, and other important variables, they can all be written in the form of a matrix. In the second year, you are going to take numerical analysis class, and in numerical analysis, what you learn this semester in calculus to doing analytically with a pen and paper, you are going to learn how to program them or how to solve those problems using well-written algorithms. And then, when you take that class, you are going to figure out, or to see it again, that really any complex operator, it can be written in a shape of a matrix, okay? Or any linear operator, that can be in the form of a matrix. For example, differential operators, d over dx, which you are going to see d over dx. This is a linear operator, okay? This can be written as equivalent to a matrix A, okay? Which you apply this one on a variable, okay? So for example, this is an operator, but you can write this one, d over dx over a variable y. It can be written as equivalently with applying a matrix A over y, okay? So let's make this also a vector. So this is to convince you, or to convince ourselves, that with linear algebra you can solve any type of complex problems. Even if you want to calculate, one of the most difficult or complex aspects that one can do is, for example, Fourier transform or Fourier analysis. Fourier transform, because most probably, you have not heard this before, but for sure you're gonna see this a lot, this Fourier transform. Even this, the mathematical apparatus of being able to express the Fourier transform of a specific function, this can be well written in the form of a matrix, okay? So linear algebra, with it you can do anything, okay? And the beautiful thing is that it is very easy when you use linear algebra. Even if you want to use to solve differential equations, I think by the last chapters of Calculus 2 in the second semester, you are going to do a little bit of differential equations, but you are going to notice that if your differential equation, if there is any level of difficulty associated with that part of mathematics, you should know that once you solve these equations with linear algebra, it's going to be much more easy. So whenever you are in the second year or third year and you are faced with a challenge, you say, okay, let's pick up a solution using linear algebra should be easier. So even here, differential equations. Even when you solve differential equations, you can use linear algebra or the principles that are incorporated with it. Okay, so this is more or less what we can do with this beautiful topic. But now, I guess you already have the syllabus. And in the syllabus, you can have a look on the topics that we are going to cover during the 14 weeks. The topics, the first one, it starts with concepts of matrices, what a matrix is, and so on. What are matrices? And then we talk about elementary row operations, reduced row echelon form. So we can add here reduced row echelon form, because, for example, whenever we have a matrix, it can be that there are some techniques which can figure out whether some piece of information is useless or redundant, okay? For example, so reduced row echelon form, it figures out if some information is just sitting there offering nothing new. So we ask whether this information is redundant. What do we mean with this one? Imagine for a moment we have this equation, 2x plus y is equal to 3, okay? But then we can have another equation which is 4x plus 2y, and this is equal to 6. Now, is the second equation telling anything new? No. So this is not good to have, because this information, the relationship between x and y, is already stated here. The second one is just, we multiply by 2 the first equation, and we're getting this. But again, as we said, it's nothing new. So it's better we say that this information is redundant. We better don't have it, because we are wasting time and space into keeping it there. And for this reason, we can use we can try to transform the matrix, the given matrix, using the reduced row echelon form. So this is how we are going to start the class. And then, if you look at the syllabus, which this is what I'm looking at. Actually, you can also check this one over on the website of the department or the curriculum. We're going to cover the solution of linear systems. Linear system of equations. So we can have a series of unknowns, x, y, z, and maybe more. And then the question is always the type that find all the unknown variables. And for this one, we can use linear systems of equations, which can be nicely written in the form of a matrix. So this will be the next one. And then we're going to learn some interesting properties of matrices, so that's something maybe I can skip. Then, what is very important next is the vector spaces. So, vector spaces, this means that a space, it can have any dimension, and one-dimensional space is, for example, a line is one-dimensional space, and an area is two-dimensional space, and the volume, it represents three-dimensional space. And in order to nicely represent these spaces, we need a basis, or we need some vectors with which we can span the whole space. Okay? So this is a keyword I want to take a note. So we can have vector spaces which can be spanned by a certain number of vectors. Then, in order to understand how a vector space can be spanned by vectors, we are going to talk about the basis. Okay? Basis. What is the basis? The basis is the minimum number of vectors which can uniquely define the specific space. We talk about the basis, and with basis we mean the following. Let me see what part of the board you can track. So let's assume that we have data represented by, or anything, or any relationship or system of equations, which is written as AX is equal to B. And this one, it can be written this way using basis 1. Similarly, we can transform this one in dx is equal to C. And this y1, y2, y3 can be capital Y1, capital Y2, capital Y3. And this whole thing, this is represented as a basis 2. So we just change the reference frame. This is one way to call it. And then we can simply transform or generate linear transformations to go from this basis to the new basis. Similarly, we can also generate inverse linear transforms, which we denote with T inverse. And then we can go back to the same data representation. So we can change from one basis to another using linear transformations. Now this is one of the most beautiful parts of linear algebra. I hope we're all going to understand this very well when we cover this in a few weeks. So this is what we're really doing here. And then once we understand the basis, we try to understand which one is the best basis. And for example, I think it's, I can offer an example right here. Imagine for a moment that we have some data points that go like this, okay? Here we have the x and y. Now, where is this point? It is projected down here, it's projected also down here, so it looks like these data points, they have an x minimum, okay, and x maximum. Then, when we project these on the y-axis, we have also y minimum, y maximum. So this is the change in x, okay, and this is the change in y, because y maximum is projected down here, okay. So we see a range over which the y is changing. Now, what can be done is the following. We can rotate this coordinate system, this xy, this Cartesian coordinate system. We can rotate it and bring it somewhere here and call this one x prime or x1, okay? And then the y, we can bring it right here, and we can see that what is the delta y? The delta y here, once we rotate the coordinate axis, is much smaller than what it was before. So in this case, we can use a basis which uses xy coordinate system, and then we can transform this one into a new basis where we have only x1. Maybe we don't need a y-axis. Maybe all the data set was in a linear system, so we don't need two coordinate system or even three. So this is the idea which is behind changing the coordinate system or changing the basis. Because if this is the case, as shown here, this means that we can simplify a problem in 2 dimensions and bring it down to 1 dimension. And this one, we call this one dimension reduction. Dimension reduction is very essential because it removes useless redundancies. We're going to cover all of these topics with examples. I'm sure you are all going to be to like these. I just need some attention from you. So after we discuss the basis or which one is the best basis, we're going to discuss in this course about eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So let's write here also vectors. Now, for a specific matrix, the best domain to analyze the system is to use the eigenvectors of a matrix. Each matrix, it has eigenvectors. So we can find those, and that means that is equivalently to finding the best basis. So it's easy. So when you come to this chapter, you should be very happy because you say, okay, now I can really find the best basis to represent my data. Now, when you look at these keywords, you know, mathematics, it has had contribution from different mathematicians. If you hear anything like Laplace, Poisson, and you are also British did a lot of contribution in science, in physics and mathematics, and you as electronic students, you are going to hear the names of the respected French mathematicians, especially Poisson, Laplace, Fourier, this guy, he is also French. So anything which is French, it's something like 200 years or 250 years old. Okay, so that's an old piece of information. But this one, it doesn't look much like French. This is more like German. And this was developed at the time when the Germans did a huge contribution to science, and mainly in physics. When they developed quantum physics, they said that we need to solve one specific type of problems, but I need to restructure the numbers like this. So they developed linear algebra. 100 years ago, there was no course at the university called linear algebra. You could not go to school and say, okay, I don't understand the equations of Dirac, so I need to take linear algebra, please teach me this. They will say, no, there is no such a course, there is no textbook on that, but which also means that this part of linear algebra, actually all of it, it's something around 100 to 80 years old piece of material. Okay? But it's a very useful one, and it is very impressive branch of mathematics. So after we do this eigenvalues and eigenvectors with this relatively new branch of mathematics, we can say that square matrices, there are some matrices which have the same number of rows and columns. Only for those we can define eigenvalues and eigenvectors. Then we're going to say, if we want to use similar concepts like eigenvalue and eigenvector, also for matrices which are not square, let me give an example here of a square matrix. Maybe I can remove this part here. So a square matrix is a matrix that looks like this. A is equal to 1, minus 2, minus 1, 3. This is a square matrix because it has 2 rows and 2 columns. Okay? We call this one square. And then we can have another matrix B, which is equal to 1, minus 1, 0, 7, minus 5, 3. This is 2 rows and 3 columns. So we have 2 rows, 2 by 3. Okay? So number of columns, we have this here, here, and here. So eigenvectors and eigenvalues, we can do a perfect job applying them here. But then we cannot find eigenvalues and eigenvector for here. So those are not defined. They are not defined for B. I mean, these eigenvalues and eigenvectors, they are not defined here, and for this reason, we have developed singular value decomposition. We call this one, so the last material of the course, singular value decomposition, or we call these SVD. SVD. Okay, so this will be more or less. Not more or less, this will be the topics that we are going to discuss. This will be the materials that we are going to discuss in linear algebra in this course. Now we talked about the textbook, and I think you can go over the same material again in the syllabus, which you can find it on the department web page. Now, if you want, we can give a short break and we can continue again in 5 minutes. Would you agree for a short break?